Well, hello everybody. Welcome to tonight's event, organized by Correlate Netherlands, which is a non-profit organization that connects data scientists and data scientist enthusiasts with organizations that advance the social good. We have about 250 data scientists and data enthusiasts in our Dutch network and over 1,000 abroad. So if you're interested in joining our network, you can find more information about that on our website, correlate.nl. But without further advertising, for tonight's program, we have 4 lightning talks by Silvan, Chiel, Muhammad, and Angelica from various different backgrounds, who will each talk for about 10 minutes each. And then we'll have a couple of questions. And afterwards, if there's still energy left, we'll head over to an online town where you can have drinks and just mingle and talk with the speakers some more if you're interested. So without further ado, I'll hand it to Silvan.
Hey guys. So we practiced the screen sharing, so this should work. So I hope you see my screen. Thanks for letting me speak. So basically I I'm 26, I live in Berlin, I'm a psychologist. I ended up with Correlate Netherlands actually because of one specific project I was interested in that was about well-being prediction. So that's how I ended up in the Netherlands branch of this about living in the Netherlands. So I'm going to speak. So I work for American digital mental health care startup, Meru Health. And they provide a smartphone-based treatment for depression and anxiety. So I don't know, there are actually quite a few competitors also in Europe available, so probably you even know some of these products. So basically most of them, and Meru as well, it contains a lot of psychoeducation, like psychoeducative videos and stuff, mindfulness exercises, CBT stuff. You have like, that's usually called like minimal guidance paradigm. So you have like chat contact with a psychotherapist who like supports you and stuff. You have Meru as a group function, which I think is also quite interesting. And finally, they have a biofeedback function. So they send, you see this on the right, they send away this sensor, which you clip on your ear, and this is monitoring it's measuring your heartbeat and your heartbeat variability, and you do like practices with it, trying to influence your heartbeat. So that's why I think like this HRV, like this heart rate data is one of the outstanding things Meru actually has. And I think it's a really interesting data set because they don't just have like this heart rate data. They also have like the depressive symptoms of their patients because they ask them regularly PHQ, which is like a standard screening for depressive symptoms. So I thought that's actually really interesting data because Meru measured this data, but also in the outside world, HRV is super easy to measure. Like every one of you having a smartwatch could measure it all the time without any additional costs. You can measure it not just like in a clinic or a hospital, you can measure it everywhere. That's pretty nice. And HRV is quite informative on a lot of processes that you can't access with like a questionnaire, like a lot of like neurobiological processes that are like indicative of depression, a lot of other stuff. People tried predicting everything with HRV. It's quite interesting. So my question, my starting point kind of was, hey, can we use this data that we have in Meru? I think it's like approximately 2,000 patients we have data about now. Can we build a meaningful application with that? And the first thing I thought of was like, hey, can we probably monitor who of the patients is doing better and who's like having improvement of symptoms and who not? Because I thought this would be a really relevant thing to know to probably offer people additional treatment or stuff. So on the right, you see how this data is collected. So if one of you is like an experimental psychologist, you will be creeped about that. There's now no standardization. We were basically just told in the morning, they get shown this and they got told, hey, lay on your back, clip on this chip, and we record the session. So I guess the first step, actually this slide is a bit too bio-heavy and research heavy for this talk. So let's be super quick. So you need to start with somehow extracting feature from the HRV data. Oh yeah, and actually it's kind of funny that some of these measurements like this SD1, which is like some measurement of so basically they're all quantifying like variability of heartbeat. Actually, that's all I want to say about it. It's not that relevant. Yeah, so let's look how the data looks like. So there are associations. It's not like So you see the associations. I wouldn't say it's like the strongest association, but probably also good to keep in mind that this is like real world data. That's like not data we have recorded in a lab or something. That's data people recorded at their home and on their own. So I think on the left, it's important to know that we have more people with lower PHQ scores. So we can't really say anything about people with really strong depressive symptoms. It's more like, I would say, people with moderate, low depressive symptoms. You see that like people with higher depression scores, they have a lower heartbeat and a higher heart variation. So this was like the simple descriptive point of view. And then the question is, okay, if we turn this into a predictive solution, how accurate could we actually predict whether a person has like depression or not? So the kind of frustrating answer is, well, actually not very well. So this slide actually looks way too simple for how much work I put into it. So basically the procedure I use is it's like a 500 times repeated 10K fold and then prediction on the test set, and then hyperparameter tuning over the cross validation procedure. And I tried quite a few algorithms. I ended up with support vector regressor and support vector machine. And well, if you see on the left, so we can kind of predict a bit if people with low scores. So the orange line is like if you just predict the mean, it's like the simple baseline. And even that super simple baseline, we just outperform really slightly. On the right, you see if we frame it as a classification problem. So like 10 is the classical cutoff for major depressive disorder. So I guess this would be like the decision point for clinicians. We get like a area under the curve like 61, which isn't that impressive. I don't know. So it's nearly a bit like reporting null results, I thought, as I summarized it, though I think sometimes it's good practice to do anyway, and also leads to some interesting questions. So the question is, so I thought like, hey, probably there are 3 reasons we could argue why this didn't work overly well. So I think the first question is the weak model. Second question is, how good is this data actually? Is it weak data? Or the third, of course, there's just a difference in how much there is like a relation in certain phenomena in the world. Of course, there's like a difference. So weak model. So basically here I just wanted to introduce some of the other stuff I tried. So particularly, which is a really interesting structure for time series hard data, is actually one-dimensional computational neural networks. So I tried out a lot with that. And it's super computational heavy and super computational expensive. And in the end, I didn't manage to outperform the support vector regressor, which I think is like a classical heuristic or thinking mistake. I always end up is like, hey, let's just use a more complex algorithm. But in the end, if there isn't more signal, you can't predict more. And probably, I don't know, probably I just didn't catch the signal. Another thing I tried, which is actually quite interesting, is dynamic time warping. That's a way how you can calculate the Euclidean distance between time series. So for that, basically, I just calculated the time, the difference between this heart rate time series between these recordings, like where did the beats appear. And then I did like k nearest neighbor clustering, also without getting to my support vector regressor. So I hope it's not the weak model. I'm happy to learn. If you have good ideas, tell me what you would do. I will try it if I'm convinced. Yeah, well, second point, weak data, pretty likely. So, I mean, of course, it's a difference whether you record in the lab or you let people record on their own. And this table I copied in there shows that heart rate variability data is super sensitive to noise. So basically what I marked there with red is like how much % of wrong beats do like significantly change the HIV metric. So you see pretty much all of them, if you just have like a 3% wrong beats, basically you have like significant biased results. So we don't have a very accurate measurement, and HIV is super sensitive to noise. So I guess that's like problem with the data. Finally, the question is, well, probably HIV just isn't overly strong related with PHQ. So I think there's definitely like evidence on like this relation, like depression is influencing like how our heart works. I think there's also, it's kind of important to see. So there's one study I see as a kind of benchmark, and there they have like 1,000 2 or 3 minutes recordings per patient. So they had like 1,000 times the data we had. They fitted a pretty nice LSTM model. They ended up with an accuracy of 70%. So I think it's also important learning for me was, so it's like start the project and probably firstly think about what is the kind of accuracy I would expect to have in the end. Because I think I wasn't really aware of that as I started with the project. Then I think also there are just phenomena that probably are just much where like the causal relationship is just much clearer. Like diabetes can be predicted super good from like heart rate data, but it's also there's a lot of evidence like how like diabetes is influencing the way our heart works. So yeah, that's pretty much it. My learnings out of this little approach. Obviously, you can't implement that. So the nice thing about working like in industry is you could implement stuff super quick, but obviously this performance isn't sufficient to do anything overly meaningful with it. I think there's still like the questions. I called it HRV and machine learning, though I think a lot of like the advantages of machine learning actually weren't really used. For example, we do all these explicit decisions on like feature extraction and data cleaning and stuff. I think if you have big enough data sets, also like actually in particularly convolutional neural networks are really good in like doing feature extraction without any explicit decisions. So I think there's a lot of stuff becoming possible if you have more data. And I think it probably didn't work as a use case for this, but I think there are a lot of use cases where it could work better. For example, I think smartwatches are a super interesting data source. There you just have so much more data that also you can be much more hard with, for example, excluding people of like or data points that are noisy stuff. So I think if I would try to build something like this again, I would probably try to do it with smartwatch-based thing. That's pretty much it. Yeah, it's still kind of work in progress. I kind of gave up the hope that it will like significantly improve, but I don't know, probably one of you knows an awesome algorithm that can convince me otherwise. And if you feel like chatting with me more about it, ping me probably in the Correlate Netherlands Slack channel or wherever you want. Thanks.
Yeah, awesome. And on time. Does anybody have questions?
I do have a short one. So your only predictor is the HRV, or do you also have information like age, BMI of the patients?
So I have a lot of more data on that. So I'm controlling the HRV effect in the descriptive part, which isn't that big. Actually, I want to write a machine learning paper about it. So there I control all the effects for age, BMI, data, sex, all the classical predictors of HRV.
Another short one, anybody?
I kind of have a comment slash question. I saw that in the neural network, you used convolutional layers and then an LSTM. But then maybe that there's some kind of a, a disharmony between the data structure and the layers that have been chosen, because I mean, what are you trying to extract with those layers? Because you have, if you have a time series data, maybe only LSTM would have worked better, because there are no like image-like data with patterns. And so you could maybe experiment with those if this is a work in progress still.
Yeah, so I tried quite a bit with LSTMs. The one problem I have is that for LSTMs you need the same. So for LSTMs, they don't scale. So basically, you need vectors of the same length. And one assumption of LSTMs, in my understanding, is that the difference between each point you feed into the network is the same. That's different to like a computational neural network. So there, I fed just the milliseconds of the inter-heartbeat intervals in. But for the LSTM, you actually need to translate the milliseconds into 0 and 1s, where like the 1s mark the heartbeat. Then you end up with, if you do it for milliseconds, you end up with 180,000 data points, and that crashed any computational power I had available.
Yeah.
So I would try it, but right now I don't know how to get it computational. So this was my problem. But good comment, thanks. Or tell me if you know how to do it. Please.
Okay.
Okay, awesome. Well, Chiel, I think you're up next.
Let me unmute myself and share screen. Can you see it?
Yeah.
Good. Let's see if I can point at thing. Oh, that's writing something. That's not what I want. Just want to point at something. Well, never mind. Okay. Does anybody know how to use the spotlight? The spotlight is not a pen, I guess.
I think you need to right click, and then there's a selection menu from which you can select the spotlight as a mouse.
Oh yeah, now it suddenly says arrow. That's not what I want. Well, let's just take the mouse pointer is enough. Okay, so what I would like to talk about is reinforcement learning. Maybe a little bit about myself. The previous speaker, I heard Silvan, you are 26. I'm also 26, but the other way around. So yeah, I have quite a history in applying mathematics. We used to call it applied mathematics or statistics or operations research. But nowadays, of course, it's all data science. When Andrew and Fabian asked me to say something about work I've done previously in my career as an independent consultant, I thought it would be nice to say something about reinforcement learning because it's, I think it's relatively unknown compared to other machine learning techniques like supervised and unsupervised learning. Also for me at that time, it was quite new, so I had to dive into it. So this is about something I did for a company together with a few people from that company to dive into how you can solve the problem they had at that moment. So what I want to show you a little bit about reinforcement learning, but not too much, and then go to the application and see what we did, because it's quite a difference whether you apply reinforcement learning to all kinds of nice computer games or situations where you can easily simulate, or when you have to apply it to a real world problem. So let's see. Get to the next slide. So I have to move my, So the contents, just a little bit about reinforcement learning. The black dots are the items I really want to talk about. But if you want to know a little bit more on reinforcement learning, you can also look at the last few slides, which I included for your for you to look at. Let's go. Reinforcement learning, it's one of the, let's say, 3 pillars of machine learning. We all know about supervised and unsupervised learning, but the third part, really, reinforcement learning, is quite a bit different. It looks at what an active agent can do in taking decisions, but sequential decisions. So let's say each time period the agent needs to do something, or doing nothing is also an action, but and maybe there are rewards on the way, but maybe not, or maybe there are negative rewards, and maybe there's a reward at the end. So if you think about playing a computer game, that you can maybe win or lose, or have a draw, that could be the end reward. But in the meantime, every move you make, or maybe there's no reward, or can be really anything from negative to highly positive. And what you want the agent to do is to learn how to play the game, or how to act in the environment optimally. So to find an optimal policy for the agent to how to operate. That's depicted in this you say that picture, but in the next one it's a little bit more detailed. So it's about an agent in an environment taking sequential decisions. Sometimes it's episodic, so there's an end to it, for instance, a game. it can also be indefinite. So then, of course, you talk about average rewards. And every time an agent takes an action, there is an immediate reward, which can be positive or negative. And there's information about a new state that the environment is ending up in. So how can an agent learn from that experience? You need an algorithm for that to really take up all the information that you get from taking an action and the changes in the environment and rewards to decide what in the end is the best policy. Oh, I go to the end. That's not good. Sorry. No, I'm not presenting. I'm just showing you the. Okay, some application areas. Of course, the games, I already talked about it, but there are many other areas like in trading or dynamic pricing. Also well known is chatbots, interacting with real people over the, for instance, on a website. Understanding, of course, what a person says is partly also text analytics, but then acting in the on that reaction of a client is also the reinforcement learning part. And then to the right, you see some applications that are more in the real world, also marketing or handling cases like legal cases or debt collection cases. This is more the area where I've worked, but also in robotics. Very interesting to see how algorithms are used to learn robots to act in a certain way, like to move in an environment or to pick up objects, or you can program a robot to really learn how to do that by just experimenting. So let's quickly go to the real life problem that I've worked on. That's in debt collection. Now, if we talk about doing good, socially good, then you can have questions about debt collection. There's a lot of in the media about people getting into trouble because of debt collections agencies. Of course, you have to assure yourself, I think, that when you work on problems like this, that these are used for good purposes and not to get people into problems. So if you see that people get into problems, you really have to help them and not like get them in worse problems. There's one, by the way, one of the reasons that the government in the Netherlands got into problems, because they are the biggest debt collectors really for people from taxes, etc. So there are many examples for health insurance, energy, traffic fines, taxes, etc. And then when you talk about the environment, you have these states, you have reward structure, you have actions, but the biggest question is, what are the probabilities of moving from one state to a next state, given a certain state and an action that the robot takes? You cannot just start running a reinforcement learning algorithm based on real interaction with clients, because a reinforcement learning algorithm will try out all kinds of different things, which maybe don't make no sense at all at the start. So it will really make a mess of it. So what we did is make a kind of simulation environment, of course, which was based on real data, to try to mimic the behavior of clients as best as possible, so that the algorithm could learn how to operate in that environment. And in the end, after several trials and doing proof of concept, we were thinking that it was good enough to start with a reasonable policy interacting with real clients for a pilot. So, in fact, we simulated the environment. You see that here, based on all kinds of characteristics of the client, the debt, but also the history of what has happened already. How many interactions have there been with the client? What kind of interactions? What was the message? How often? How long ago, etc. You can determine what is the probability if I take action A, B, or C that you get a payment, or that the whole process stops, or any other next stage that you can get into. Some results we got. I had to take out the vertical axis because yeah, since it's confidential, but what you can see here is that if you let a robot just take random action, that's the bottom line here, you don't get a very good result, of course. If you look at the purple one, which says DIR, that's the policy that they used, a kind of standard policy. Let's say you send a letter on the first day, you send a follow-up email after a week, and very standard, so not at all fitted to the specific client or debt. And then you see the red line with a confidence band around it. The confidence band comes from all the different simulations that we do. So we run a simulation many times, and then you, of course, you get different results. But this is the general trend. You see that it picks up. It has to pick up from a low level until it really understands what to do in which case, and it goes up and up, and it just goes on, and it keeps on learning. And the blue one on the top is what if you would let the policy that it has learned after 10,000 files, if you would have used that from the start, then you would get this result. So you see, you can really learn a good policy, how to interact, and to do it better. So maybe, and there you have to look at what the policy exactly entails, is maybe it is the idea that, for instance, younger people, you send messages via WhatsApp instead of writing a letter, or maybe you have a quicker follow-up, or well, there can be anything, but you target it more to the specific debtor. Later on, we did it a bit more sophisticated. We used a neural network for a function approximation. So the function I'm talking about here is the function that gives the value of a certain state and taking an action in a certain state. You can use that in a tabular form, but if there are many states and many actions, that becomes impractical. So you can do, for instance, linear or nonlinear function approximation, or you can use a neural network for that. So then it works quite good. And you also see that now it learns much faster, because in the previous slide we had used 10,000 files to get to a result, and now it goes much quicker. Let's see, I'm running out of time, I think. So just quickly, if you look at the blue bars here, you see that the net result is quite a bit better than in the DIR, which they used to do. In different 3 different algorithms that we used. The right one is with the neural network. Some practical aspects. We did several proof of concepts. We started very simple to understand how it worked. Then made it more complicated until we were really in a realistic setting, and then we could run a pilot, which was, by the way, a big implementation effort, because you can do all kinds of nice things in your lab, but if you really want to apply it and attach it to real life systems, then there are a lot of problems there. We started out doing everything in R, because most people working on this were very experienced with it, but later it proved that it's much better. By the way, if you want to use Keras or TensorFlow, you have to use Python anyway. Even from R, you go via Python to Keras or TensorFlow. And later we switched to Python because there's much more example code available for reinforcement learning in Python code. So it's much more practical to work in Python. It took us about 2 man-years together to with 3 developers to make this from scratch. And a few takeaways, and that's my last slide. It's quite a complicated technique. There are many different algorithms and add-ons that you can use for different algorithms. One, Q learning is a very well-known one, but you can have all kinds of bells and whistles to that. So you also end up with many hyperparameters, especially if you also have a neural network behind it. So, and then because running this simulation like this takes a lot of time, it also takes a lot of time to find out what your best hyperparameters are. And you really need to tune it to your specific problem. So that's quite complicated. Well, the last 2 points I already mentioned. You really need to simulate first, because you cannot just start running your algorithm with real clients and get all kinds of very strange results. So I think that's basically it. Yeah, also the last point is that the communication with business, it's often very difficult to explain what this algorithm really does, especially these kind of algorithms that keeps on learning with their own experience. People are quite reluctant to just implement it and let it go. I can imagine also, because you really don't know which direction it will head. It's like stepping into a self-driving car, where you know that it maybe it has learned all kinds of situations, but yeah, maybe not the situation that you will encounter. So do you really trust it or not? That's, I think, what I wanted to say. Yeah, start in Python. That's a good thing. So the rest of the slides are more background on reinforcement learning. But I think, yeah, that's too broad for this presentation now.
Okay, well, thank you. Because we're a little behind, let's go directly to Muhammad, and then if anybody has questions, you can do that in the online town.
I see a raise of hand. Can you hear? Can everyone hear me?
Yeah.
Okay. Thank you very much for this opportunity to present the work that I'm currently doing. So it's a little bit abstract from the presentation that you had before. So yeah, I'm currently really working on these concepts and also developing different kinds of definitions. So currently, I'm Muhammad Salim. I have an experience with spatial data quality. So it's really about space and how the maps are built, and cartography and different kinds of visualizations. I did my master's in spatial engineering from Faculty of Geoinformation Science in the Netherlands. I got connected from Coral 8. It's like I was interested in data quality stuff, and I got really connected to them, and then I subscribed to them, and then I learned about this event. So the topic is basically the open data. So what's open data for me? And this is for my definition is that it's fair, it's findable, accessible, and interoperable and reusable. And this is often used in when we talk about spatial data in our world, in geodata world, in geoinformation science world. It should be, we can find the data and it's accessible for the users, and it's use similar vocabulary to so that all data could be integrated and it could be reusable. But what often missing is that in spatial data, we need to communicate with different actors, different stakeholders that actually don't understand a lot of standards that we use in the spatial data infrastructures. So I will discuss a little bit about that. So first, I think that we have a wide range of audience. So first I will explain a little bit about what is spatial data. Spatial data is like a geodata with a georeference with a map. And then with the map, you have different roads and different attributes of the roads, and this road or what this building stands for, and then how this is related to another objects on the real world. This is basically spatial data. Spatial data, it's really used when it's in disaster times, that how many people in need of aid, how many people are affected or could get affected, and different types of hydrological and also earthquake modeling use spatial data to know where is something wrong and where we can intervene. So spatial data is, in conclusion, is very important for disaster risks and building resilience. Spatial data have different kinds of standards: ISO, OGC, W3C, and ANSI, and IHO, and WSI. These are all the standards that are used in spatial data infrastructures. So if we see how the data is complete in Google Maps, if you live in Netherlands, you can easily get access to all the street views. But if you live in Global South, as you can see, it's really less accessible and data is not really there. But they have other reasons as well. But there's also a reason that the data is scarce and data is not really contributed to it. People don't really contribute to it. But still, Google is, because normal people, common man, cannot really contribute to Google in that manner. So it's still kind of, we can say it's a closed source. But there's another source, it's called Openstreetmap. This is being highly used in the case of Global South, and it's used for a lot of purposes, more mainly because of its openness and free and to use, and anyone can go and make an account and edit it, literally anyone, and can add data, and yeah, and that can be downloaded and can be exported. The problem is with the quality of the data. If anyone can add it, it becomes heterogeneous and the quality becomes really low. And the quality, completeness, temporal quality, or usable quality, it depends. So let's take an example, that how one of the example of the use of OpenStreetMap. Then I will explain that how it could be improved and what I'm going to work on. So there's an open route service. Open route service is that navigation from, if I want to travel from one place to another, just like Google Maps, but it's open source. So if someone wants to go from one place to another, what are the components of knowledge that you have to use to know what's going on in the map? Firstly, it's like 7.4 kilometers or the duration. One of those two things you have to know in order to get from one place to another. You know, because we live in a global north, we know what's kilometers and what hours and what minutes and seconds are. We can easily navigate from one place to another. But imagine that people that does not know about kilometers and minutes and seconds, people that are living there, we're not contributing to them as well. So in other sense, we call the data that is non-standardized as dirty data. It is non-standardized, outliers, and incorrect records. That's how currently in spatial data world we classify the dirty data into. But usually it's the local knowledge. It's also considered as non-standardized representation, which is wrong in my opinion and in my research as well, that non-standardized representation can be considered as valuable local knowledge. And local knowledge is fast, understandable, and it's increased the rate of innovation. Imagine like you're doing a math test. If you don't know anything, the math is very hard. If you know that equations that you're working in, math is easier and it will increase your innovation and to work on it. So now I will imagine a scenario, same scenario with the Mali case. Imagine there's a scenario with a water crisis in Mali. Relief work started. Water sources are shifted from one place to another, and you need to tell people to go from one place to another. But currently, the maps that are provided use kilometers and all the standardized spatial data infrastructures. Then what happens is you need to time to explain it to them that, okay, this is kilometers, it should take this time, and you have to, maybe first you have to translate, and then you have to use different kinds of sign languages to tell them. It's not fast, it's not efficient. So maybe instead of that, we tell them that, okay, these are, because ladies in those regions, when they go and take the water, they usually talk about the gossips and stuff, and they talk about all the day, and they know only these knowledge. They don't have knowledge about kilometers and what the numbers are, even. So we can tell them, okay, this is 2 gossips away. You can talk to your fellow 2 gossip, and then you can reach the destination. So this will help them understand that what actually it will help them use their own local knowledge and their own local experience to know what the data is and know what the directions they are going and how much time they would be needing. Or some people are quite knowledgeable, they can use this 20 footsteps. So we have to integrate these into our data standards instead of following them as a non-standardized representation. So it can, yeah, as I mentioned, fast response, informed decision, and it can help for innovation as well. This is where I'm working in. I am redefining these quality concepts, because if we define the quality, then we can define the different standards that we will use for spatial data infrastructures. And I am working on defining these and then practically applying it using open data and how it could help in building resilience, because once they're using their own local knowledge for their own from their own knowledge, instead of learning from other people and following their standards, they will follow their own standards and they will feel more comfortable with it. And I want to define these kinds of quality definitions which would benefit them as well for the resilience. Thank you very much. And if you want to connect with me, I'm currently looking also for the fundings. If you have some tips for it and for my research, you can always contact me. Thank you very much for this opportunity.
Thank you, Mohammed. That was fascinating. Any questions?
So it might be a bit of a random question, but I'm really stunned. Why is Google Maps available in whole Europe, but not in Germany? Any chance you know? Because this just really catched me on the Google Maps map.
Yes. It's because of data privacy. It's really well loaded. Because if you see in the east of Germany, you know what happened in East Germany, right? So there's more or less data. So if you go to West Germany, like in North Westphalia, you have more street view. So it's really about the personal preferences, huh? Because people in Germany are really strict to the data protection.
Thanks.
No problem.
Any other questions?
Okay. Thank you very much. I think there's no question, but you can always ask me and connect to me.
Yeah, excellent. Well, then we've made up for some time. Let's go to Angelica. You're up next.
Time for me. All right, let me share. Right. All right, can you all see my slides?
Yep.
Yep. Okay, cool. Then, yeah, my name is Angelica Stefan. I'm a PhD student at the moment at the Psychological Methods Department at the University of Amsterdam. Like the topic that I'm working on is mostly Bayesian statistics, so this will also be something that I will mention today. But mostly I'm here today to get to tell you a little bit more about one of my favorite topics in data science, and that is sequential hypothesis testing. And in the next 10 minutes or so, I'll give you a brief introduction into sequential hypothesis tests or sequential designs and show you how they can help you answer the questions you're interested in with as little effort and costs as possible. Let's get started. Now, if I look at tasks or problems that data scientists are confronted with, I think there are two fundamental categories. Either there's much data. Some would say too much data or big data. And in this case, our job as data scientists is to find ways to manage the data and to make it searchable and to find meaningful patterns in the data. And sometimes, as we've heard before, to use it to make predictions. And the other fundamental problem that we can be confronted with is that there's too little data. And this happens if we have an important research question that we are interested in. For example, which of these products do consumers prefer? Or does this new medicine work? Or does this new fitness app that we developed help people achieve their fitness goals? And usually, well, there's not exactly the data that we need to answer these questions right away. So in this case, our job as data scientists, I think, is to nail down that research question and to figure out what kind of data would be needed to answer the research question, and then to collect that data, or at least to organize data collection in some way. Now, the issue is data collection is typically connected to pretty substantive costs. For example, if you're conducting a survey, you may need to compensate participants or interviewers. Or sometimes you need lab equipment like test tubes or Petri dishes, or you need to pay rent for testing rooms, for lab spaces. And in the end, you might need to pay someone for data entry, or you spend a lot of time yourself trying to type numbers into your computer. And as you can see from these examples, data collection can be very costly. And typically these costs are proportional to the amount of data that you collect. And which means the more observations that you collect, for example, the more participants you include in your survey, the more money and time and effort goes into that data collection. Now, we're all living in a world where resources are scarce and our budget is not endless, and efficiency is an important factor when you're planning a study. But what exactly is an efficient study design? Efficient study designs can strike a balance between collecting as few observations as possible and as many observations as necessary. So if you're planning a study and you only have finite resources at your hands, it is important to find this balance to collect just as many observations as necessary. Now, of course, the question is always how many observations are enough. And so what you would usually do if you plan a study is to find a sample size and to fix this to a certain number before you conduct a study. Say, I want to collect data from 100 participants in a study. And then you collect exactly that number of observations, or at least something very close to it. But this is not ideal from the viewpoint of efficiency, because the sample size that you determine before you see any data crucially depends on what you're expecting to see. And we all know that expectations can be wrong and there are always surprises. So for example, the effect might be smaller than what you expect. And in this case, the sample size that you plan for is probably not large enough to detect the effect. That's bad, because then your data is essentially worthless because you couldn't show that the effect was there even though it was. But what could also happen is that the effect is actually bigger than you think. And in this case, you could have detected it with a much smaller sample size than you used. And in this case, you wasted resources on data collection because you could have come to a conclusion much earlier. And this is exactly the problem that sequential designs tackle. They allow you to stop more or less exactly when you found the answer to your focal research question. Now, how does a sequential design work? You start out with a minimum sample size, and this minimum sample size can be really small depending on the type of analysis that you use. Then you check a certain stopping criterion. I'll show you an example for this later. And if your stopping criterion that tells you whether you collected enough data is not fulfilled yet, that's okay. Then you just collect an additional sample of a certain size, say one more observation, and check the stopping criterion again. And then you continue in the circle until at some point your stopping criterion tells you, okay, and now you can stop, and then you stop data collection. And then you go forward, analyze your data, make your test decision, come to your conclusions. And this is the basic process for pretty much every sequential design that you will encounter. And there are actually a lot of them. Even though a lot of people aren't really aware of them, there are a lot of sequential hypothesis testing procedures out there. And there's at least one for every flavor of statistics that you prefer. Frequentist, Bayesian, likelihoodist, you can just really make your pick. One family of sequential hypothesis testing procedures that I personally really like are sequential Bayesian designs. So I'll talk a little bit more about them. One typical design is sequential testing with Bayes vectors. And I want to use this as an illustration for what exactly sequential design can look like. First of all, what you need are two Bayesian models. Now, what is a model? A Bayesian would tell you its likelihood and priors, but for now, we don't have to get into the specifics. We can just think of it as a mathematical representation of your competing hypotheses. For example, take a new fitness app that you developed and you're interested in whether people feel healthier after they've used it regularly for a month. And your competing hypotheses in this case would be, yes, it works, people feel healthier, or nope, it doesn't work. They feel exactly the same way, or even worse than before, which would be bad. And now you can represent these two competing hypotheses in two competing models. That's the first thing you need. The second thing you need before you start is a stopping rule. And this is where the so-called Bayes vector comes in. A Bayes vector is a quantity that tells you how likely it is that your data have occurred under one model versus the other model. And a Bayes vector can be interpreted as evidence in favor of either model. So for example, in favor of the model that your app worked, or in favor of that the model, the app didn't work. Now, you define two thresholds and see whether the Bayes vector crossed these thresholds. So this basically means we stop either if there's sufficient evidence for one model or if there's sufficient evidence for the other model. And then we can, if we have these things, we can go about doing our data collection. We start again with an initial sample size, here that's 10, more or less randomly, and check the Bayes vector. If the Bayes vector hasn't crossed any of these two thresholds, we collect another observation, and another one, and another one, and another one, until finally the Bayes vector here crosses one of the thresholds, and then we immediately stop. And so this is how a Bayes vector, sequential Bayes vector design works. And there are a lot of things I think to like about this procedure. First of all, it's incredibly efficient. You stop exactly at the point where you're ready to make a decision. But there are also a few other advantages in this procedure, also compared to other sequential testing procedures. So you don't have to specify the number of times you look at your data ahead of collecting the data, for example. You also don't need to specify a maximum sample size if you don't want to. You also don't need to exactly know how big the effect is that you're looking for. So it's just very flexible. However, as with all sequential testing procedures, there are a few things to consider. And I think the most important practical consideration if you're using sequential designs in practice is that you need to make sure that your data won't be biased. Now, why can this be a problem? Just imagine you check the development of the Bayes vector again and again and again, and then it's just so close to the thresholds, and you really wish you could stop the data collection to finally get to your final results and come to a conclusion. And this is kind of a really big incentive to influence your participants in the right way, for example, or to look at your data and clean outliers in your data in a certain way that it fits your purpose, or just in other ways to influence your results. And this doesn't always have to happen like consciously. This can also be something that just happens on the way. And so one way to get around this, at least a lot of these issues, is to use blinded analyses. That is, mostly just have someone keep track of the stopping criterion who doesn't know about the purpose of the study or is not as invested as you are. And you can also, for example, another way of doing blinded analyses would be to automate the interim analyses, so that, for example, your survey will be automatically pulled from a platform once your base factor crosses the threshold. However, these are all details of the implementations, and I think it's really worthwhile to just try it out. And if you got curious about all the possibilities of sequential designs, and you want to learn more, I think a really good resource that I can recommend is this sequential testing website that some of my colleagues from the University of Amsterdam put together. And it contains a lot of information, preprints, papers, some more history about sequential testing, and it's, I think, a very good starting point for reading more about sequential analyses. Yeah, you can, of course, also always reach out to me. You can send me an email, find me on Twitter, and just ask questions. I'll be there in, after the talk. And yeah, thanks for your attention.
Awesome. Thank you, Angelica. Anybody have some questions?
I have one, though I already asked one, so I would just ask if no one else asks. So so this was really interesting. Can you repeat, or probably, I guess the interesting point is, why is like p-value hacking, or like why isn't it a problem to check the results over and over again compared to frequent statistics? I guess you get asked this question all the time.
Yeah, and it's a very good question. It's kind of counterintuitive if you present it this way, like, oh, it sounds a lot like optional stopping, something that you shouldn't do, and something you would really run into problems with. But all of these sequential designs that I mentioned on this one slide, I can show it again, they actually correct for multiple testing in some way or other. So in sequential Bayesian designs, we just basically we don't care about error rates, but the base factor is immune to these problems of multiple testing, because it doesn't depend on data that we haven't observed yet. In other, for example, in frequentist approaches, like for example, alpha spanning approaches or group sequential designs, these are methods that are developed to still control the error rates and the designs, and to make sure that your alpha error rates don't accumulate in the way that they would do if you didn't correct for it. So all of these methods have specifically been developed to counter exactly this problem.
Any other questions?
Yeah.
Yes.
Angelica,
Yeah.
I guess you also run the risk of continuing indefinitely, because you keep you stay between the lines. So you probably generally also have a stopping criterion in the number of observations that you, or maybe you're stopped by your budget, I don't know, but
yes. So mathematically, you would always stop at a finite sample size because the base factor in this specific design, if your sample size goes to infinity, your base factor also always like goes to one of the thresholds. And since you you set your thresholds at finite values, you will also stop at a finite sample size that is before infinity.
Yeah, but if
in practice, that's of course
10 million,
I mean,
then you have a problem.
Yeah, so in practice, this of course may not help because smaller than infinity is still a lot of resources that would go into that. Yeah. So what you would do in practice is to just set your maximum sample size at some like maximum number of observations that you're willing to collect. Yeah. So that would basically be the budget that you have for this study, the maximum budget.
I guess it also holds that if you say beforehand, if I don't discover it in 1,000 or 2,000 observations, then it's probably not worthwhile because then it's probably the effect is so small that.
Yeah, exactly. Yeah. That's just another stopping criterion you can impose.
Yeah.
All right, excellent. Well, then I want to thank all the speakers again for this wonderful session.